Starting 9.4, it's the last one of chapter 9. We're doing the geology of Mars, Venus, and the Earth. I meant to add on the Earth there. Okay, so let's go forward. Okay, cratering on Mars. If you look at Mars, you can see there's a lot of cratering going on in different areas. It looks like the northern part doesn't have as much cratering as the southern part, leading us to believe there might have been some oceans or maybe lava flow in those areas. Okay, many earlier craters that were in those northern parts were deleted or erased by the erosion that was happening from the lava or the water. Okay, there are volcanoes on Mars. The largest volcano in our solar system is on Mars. It's called Olympus Mons. Right there, you're going to need to know that. Olympus Mons. It is what we call a shield volcano, which means it has medium viscosity type lava coming out of it. It's not very like honey-like, and it's not very watery-like. It's kind of in the middle. Okay, next thing, plate tectonics. We can see features on Mars leading us to believe that there might have been plate tectonics in its earlier life, but we do not believe that those are happening right now. We do see Mars quakes, so we think that there are maybe mild plate tectonics going on, but nothing anywhere near as severe or not severe, but detailed as Earth, okay? So, on Mars, we do see lots of examples of how we know it had water in the past, okay? We can see dried up river beds, as you can see the oxbow formations there. We can see lots of different places that might have been filled up with water. We can see craters that have eroded from water use. And we can also find in these riverbeds rocks that are have been rounded, like you might see in river rocks here on Earth. And we believe this would have happened from erosion from water. Okay. Okay, what shaped Venus? Okay, Venus. We don't know a whole lot about the surface of Venus because it's very difficult to see through its atmosphere, because remember, it's so dense with greenhouse gases. So the only way that we see the surface is we use radar mapping, and this is how we can determine what's on the surface of Venus. Through this, we have seen that it has fewer impact craters. This might have to do with the denseness of its atmosphere. Maybe not a lot of smaller craters could reach the surface through its very dense atmosphere. Okay, we do see volcanoes on Venus, leading us to believe that there probably is a active magma core, like a mantle like we have. Now, something interesting that some of you guys might not know is that we have landed, not America, but Russia has landed a lander onto Venus, and it took pictures, and it didn't last for very long because of the heat and the atmospheric pressure. But here's one of the pictures we got off, and from that we can see that there's very little erosion going on in the areas that we were able to see. Okay. Now, does it have plate tectonics? You would assume the answer would be yes, because it's so similar in size to Earth. So you would assume it would be very similar in terms of plate tectonics. But we don't see anything really happening with the plate tectonics. We think it might be because it has a weak convection going on in the center, okay? So maybe it has a very thick lithosphere. We're not too sure why we don't see plate tectonics going on with Venus. Okay, so plate tectonics that have shaped Earth's surface. So this is the number one thing that has shaped our surface, is the plate tectonics that happen. Motion, we've spoke about it before. Motion can be tracked through GPS. And we see that these plate tectonics move anywhere from a couple to many centimeters per year, okay? Just depending on which one you're talking about. Remember, certain areas will have a stronger convection going on below it in the mantle, and that would cause it to move faster and in different directions, yeah? As you can see here, they are showing which direction these plate tectonics are moving, and those would have everything to do with the convection going on underneath the lithosphere at that point. Okay, so how do we know that this stuff is true? We can kind of like put together these continents like puzzle pieces. Now, obviously, they aren't going to be exact puzzle pieces because there's been a lot of years that have gone into moving these things, so they've changed a lot over the time. But if you can see here, it looks like these things fit together. You can fit Africa, and it would fit right here into here, and like that part of North America would go right there. You can see that kind of fits there. It's like a puzzle, and this is how this was kind of discovered and put together. Okay, so we have two types of crust. And remember, we spoke about the crust being the outer part of the earth. There are two parts. There's the part underneath the ocean, and we call that the seafloor crust, okay? The seafloor crust. It's very dense, and it's not as thick as the continental crust. The continental crust is what we're on right now. It's the land, okay? It's the stuff that doesn't have ocean over it. And from doing this, noticing that there's two types of crusts, what we know about this oceanic crust or the seafloor crust is that it's much younger than the continental crust. So we know that this gets thrown into the mantle and recycled quite often. So the bottom of the seafloor crust pretty much recycles, we believe, about every 200 million years. So the entire ocean's floor will be different in 200 million years. It will be different magma that has risen to the crust and cooled down and solidified into rock. Okay, and that just keeps recycling. Part of it goes in and then gets recycled, and we call that subduction. And I think I have a picture of subduction right here. Here it is right here. So here's the seafloor crust. It runs into the continental crust and gets pushed down into the mantle where it's extremely hot, right? It burns this part that's in here and it breaks off. And over here on the far side over here, some of the mantle is getting recycled into the seafloor crust going up, creating new seafloor crust, okay? And this is the continental crust that it does not do anything like that. What we have on the continental crust is what we'll have millions and millions of years from now, okay? As you can see, we have different things here. We have ridges where the mantle or the magma is coming out. And this is how we get created, yeah, on these plates. Okay, measurements of these plates tell us that we've been separating, right? This is called Pangea about 200 million years ago. And through those 200 million years, you can see where we've arrived today. Okay, so I think this is the last slide. Yes. So hot spots. You need to know what a hot spot is. A hot spot is a part in the crust where the mantle was so hot. Okay, it was so hot in a certain area that it burned through the crust and pushed out like a piece of land or volcano, and we call these hot spots. And we have like Yellowstone is a hot spot. Hawaii are hot spots. And these are places not where the plates aren't like defined out. Like let's see here. Like here you can find places where lava might come out. On these areas you find lots of volcanoes across these Andes and mountains and things like that. But a hot spot is where it occurs kind of in the middle of a plate, where it's just so hot it burns through the lithosphere, okay? And it creates its own like volcanoes or different hot spots in there, like Yellowstone right here. And that's what a hot spot is, yeah? And so that is everything for 9.4.